Hello, we are back again investigating more information regarding inverse functions. This is the second part of this lesson. Our next question is, do inverse functions always exist? So in our previous video, we learned how to find inverse functions. We learned what it meant to be inverse functions, meaning x and y are swapped, and we also learned what that meant to find it algebraically. So now, are there situations where we can't find our inverse function? Or is it always possible to find an inverse function? No, it's not always possible. For a function to have an inverse, it must be a one-to-one function. But do we remember what one-to-one means? If you forgot, that's okay because I'm about to remind you. First, that means that y's do not repeat. Remember, for an equation to be a function or a relation to be a function, x's do not repeat. So now, for it to be one-to-one, we have to add an additional stipulation, meaning y's do not repeat either. So, for a graph to be a function, it must pass the vertical line test. For a function to be a one-to-one function, it must pass the horizontal line test. So, you're going to test it vertically and then horizontally. So, let's look at what this means. So, we have a parabola. We know that parabolas are functions. We know they pass the vertical line test because we have been through several lessons regarding functions already, and we've looked at parabolas for examples. So now we know it passes the vertical line test. So now we need to test the horizontal line test. So here's my horizontal line, and we begin the test. It has failed the horizontal line test continuously since the line started moving, but I stopped it here to show you why it fails the horizontal line test. The horizontal line crosses our parabola in two places. So this is not a one-to-one function, meaning its inverse is not a function. So let's see what that means, why that is the case. So we know for a function to find its inverse, we have to reflect the function across y equals x, the line that you just saw appear across your screen. So we're going to reflect this parabola. It is now reflected. So the green line, our green parabola on its side, is what is supposed to be our inverse function. Well, we have one on our graph, so why are we saying that this inverse function does not exist? Let's see if it's even a function to begin with. Here's our vertical line. Does it pass the vertical line test? Absolutely not. Continuously, since the line started moving, it has continuously failed the vertical line test. Here we see one instance where it has failed the vertical line test. So this is what it means whenever we say that the inverse is not a function. Or a function does not have an inverse, meaning it does not have an inverse defined over its entire domain. But what if we want to find the inverse of a function anyway? We can restrict the domain where the inverse is indeed a function. So let's look at a quadratic function. We know this is a parabola, so we know it doesn't pass the horizontal line test. So here's our parabola, but very similar to the one we saw on the previous screen. Here we have our vertex. We're trying to determine how can we restrict this parabola. What can we do to this function to make it where we can find an inverse that is indeed a function? So here is our vertex. It's -1, -4. Why is this vertex important? It is important because this is the turning point. If we take the function and we split it in half at the vertex and we erase one half of the function, then we have a function that does indeed pass the horizontal line test, okay? So you get to choose, but we're going to limit the domain. So in this case, I'm going to say I want to work with the positive side. So I'm going to say that the domain is going to be greater than or equal to -1. You could have very easily said less than or equal to -1 as long as it was on one side of the vertex or the other. Now, we've restricted the domain, so how does that restrict the range? Well, the range is what the range is because this is a parabola. In other instances, it may change your range as well. Maybe for a cubic function, it changes your range. So our range is y is greater than or equal to -4. Now, we want to find the inverse. We know that we have to swap the x and the y. The vertex is -1, -4. So if we swap the x and y, what is the vertex of the new inverse function? -4, -1. Yes. Let's find another point on our original function. We have a y-intercept of -3. So if we swap our x and a y for our inverse function, we now have an x-intercept of -3. And now remember, we are only looking on the right side of this parabola because we have limited our domain to anything that is greater than or equal to -1. Let's find another point. We have an x-intercept at 1. So on our inverse function, our y-intercept is going to be 1. Lastly, we have a point 2, 5 on our original function. So on our inverse function, we know that point is going to be 5, 2. We are now going to connect these points with a nice smooth curve, as smooth as I can get on this program. And that is going to be our inverse function. So we found an inverse function based off of a restricted domain. This function does pass the vertical line test, so it is an inverse. It is an actual function. So what is the domain of this function and the range of this function? So we know our domain of our original function was greater than or equal to -1. X is greater than or equal to -1. We also see that our range is greater than or equal to -1 for our inverse function. Our range for our original function was y is greater than or equal to -4. Now our domain for our inverse function is x is greater than or equal to -4. So once again, our x and our y's have swapped. And you can notice that with our domain and range. They have swapped as well. So that's how you find the inverse function, by restricting the domain for a function that is not 1-to-1. This is our last video for our unit functions. I hope you have enjoyed this unit.